I am going to show you today this algorithm that hypothetically or theoretically is like an extension of this algorithm, but it gets this interval to have width 10 to the minus n, so it gets like n digits of accuracy in about 10 to the n steps. But let me tell you the intuition for this algorithm. Or I'll tell you even the sketch of the algorithm, and then we'll make it an accurate sketch soon enough. So the intuition or sketch of how we're going to get thousands of digits of accuracy. Okay, suppose the angle theta we're estimating here. I'm really going to, as I said, think about it as some fraction of a full circle. So suppose it's like 0.32695 tau, like 0.326 fraction of a circle. And actually, let me just write out the digits: d1, d2, d3, d4, dot, 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 dot. Okay, that's the decimal digits that we're going for. And I'm really going to try to figure out like the first 1,000 digits here. Seems crazy. Well, step one is going to be apply this algorithm. So we're going to apply interval estimate to our mystery rot. And what does that basically do at a high level? That gets us 0.001 tau accuracy. So it basically gets us the first 3 digits. Okay, so this gives us, I'm being a little imprecise here, we'll be more precise later, but this gives us like d1, d2, and also d3, maybe like a little uncertainty on d3. Does that make sense? Okay, so we're like, great, we got 3 digits, 997 digits to go. Okay, but now here's the idea. Let's think about mystery rot to the power of 10. Let's think about, imagine doing this mystery rotation code 10 times in a row. Well, this rotates by 10 theta, which is d1, d2, d3, d4, dot, 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 full circles. But now here's the trick. This is like, maybe this is like 7 or something, or 3. That's like 3 full circles plus this fraction of a circle. So this is the same as 0.d2, d3, d4, dot, 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 tau. Okay, if you really rotate by 10 theta, like it'll go around the circle like d1 times, and then it'll go like this fractional amount along the circle. So then we're like, oh, great. Now we'll do interval estimate on this thing, and we'll learn these 3 digits. Okay, so we'll do, interval estimate on mystery rot 10. And we'll learn d2, d3, and d4. Maybe there'll be like a little uncertainty on d4. And actually, we're like, well, we kind of already knew d2. d3, we were a little bit uncertain about, but this will firm up our certainty. And now we pretty much know d4, a little bit of uncertainty. We're like, oh, we kind of got 4 digits now. Okay, now you might guess where I'm going with this. The next step is think about mystery rotation repeated 100 times. This rotates by how much? d1, d2, point d3, d4, d5, d6, dot, 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 dot. Full rotations, which is the same as just the fractional part. Okay, I'll make this more precise, or we'll sort of do an example later. Great, so effectively, this mystery rotation just rotates by this fractional amount of a circle, a full circle. So if we do interval estimate on it, we get D3, D4, and D5. Basically D5. And again, we're like, well, we pretty much knew D3. D4 we more or less knew, but like this sort of fully confirms it. And now we have like almost full confidence on like D5. There's a little bit of cheating going on here, which I'll get to later, but not much. And we repeat. And like every time we do this, we get another digit of accuracy. So if we want 1,000 digits of accuracy, we'll just do this, idea. This is 3 times. We'll do it 1,000 times. Now, there's some issue with that, of course. We get up to the nth digit, and think of, n is like 1,000, the nth digit, via interval estimate applied to the mystery rotation, done 10 to the power of n times. Okay, maybe like n plus second digit or something, but something like this. And I indeed claim to you that like this whole sketched algorithm here uses only about 10 to the n steps, or 10 to the n work, which is what I'm saying here. Again, that's kind of a crazy amount, but just to quickly justify it, this overall number of calls, total number of calls to mystery rot here. Well, every time we do interval estimate, it's like some 120,000, but okay, that's a constant. But then, okay, we do it on mystery rot. We do on mystery rot to the 10, but to implement this, you just have to run the code for mystery rotation 10 times in a row. So that's 10. And to implement this, you have to run the code for mystery rotation like 100 times in a row. And then you have to run it 1,000 times in a row. And at the very end, you have to run it like 10 to the n times in a row. Okay, and what does this add up to? Well, 1 plus 10 plus 100 plus ... plus 10 to the n. It's basically 10 to the n. It's like negligibly more. So this is order 10 to the n. So again, you're like, okay, this would be cool if n was like maybe 3 or 4 or 5 or 6. That might be okay to do on my quantum computer. And it would be like a quadratic speed up over like what you would get using classical ideas. And in fact, you can put this together with Grover's algorithm and and thereby get an algorithm that's really good at estimating the fraction of satisfying strings up to, 5 or 6 digits of precision. But doesn't seem practical. But now here's the twist. When we use this glorious algorithm to get n digits of precision to theta in the factoring algorithm, which will come up later, we'll be in a funny situation where shall I write it? Where we know how to do mystery rotation 1 billion times or 1 zillion times in way faster than 1 zillion steps. We'll actually know how to do, this instead of in 1 zillion steps, in like n steps, and n is only 1,000. So we'll have this like crazy, like sort of for each power k, we'll have like a super sped up way of doing k rotations that's like way smarter than just literally running the code k times in a row. So in the factoring, when we get to it, when we eventually get to it, we'll have some particular mystery rotation in mind that has to do with the number we're trying to factor. We'll know how to implement mystery rotation to the k efficiently, even if k is like 10 to the 1,000. And where by efficiently, it'll be like, I don't know, 1,000 steps or something like that. And therefore, by plugging in this into this algorithm, instead of taking 10 to the 1,000 steps, we'll take maybe 1 plus 2 plus 3 plus 4 plus 1,000 steps, and that's fine. And how could this be? You might say, like, what kind of bizarre situation is this? It's not so bizarre. For example, let me just give a slight analogy. Let's say, put yourself in the mind of classical computer programming. In classical computer programming, maybe you know some simple, efficient code for increment. That is, taking a number x and converting it to x plus 1. Okay, like in Python or whatever, you just like add 1. But if you think maybe about like, logic circuits, you have to like implement some minor circuit that like incremented a number, but still it would be easy. So then suppose I said to you, what about like doing increment 10 to the 1,000 times in a row? You could implement that by running your increment code 10 to the 1,000 times in a row. Well, in theory, but 10 to the 1,000 is like enormous. That would never end. But you actually would say to yourself, wait a minute. Then the operation of incrementing 10 to the 1,000 times in a row, this is just doing x maps to x plus 10 to the 1,000. And I could write separate different code for this. And my separate different code for this is just a 1,000-digit number. My separate code for this would also be efficient. Like adding two 1,000-digit numbers, it takes like 1,000 steps or something. That's fine. So I'm just trying to bring this up to like illustrate that like you can maybe conceive of a situation where you have some code, and now you need efficient code that is equivalent to repeating your code 10 to the 1,000 times, but the complexity of your code will not be 10 to the 1,000 times the complexity of the original thing. It'll be like much, much simpler. This will happen in a factoring algorithm. It'll almost even be like this. The code in the factoring algorithm will be like doubling a number mod b, where b is the number you're trying to factor. And so doing it 10 to the 1,000 times in a row is like multiplying by 2 to the power of 10 to the 1,000 mod b, the number you're trying to factor. And this is like a modular exponentiation, which, as you might know, can be done efficiently. Okay, this is all like a preview for what's eventually going to happen. But yeah, I wanted to set this up. So what we're going to do, in the rest of the lecture is kind of go over this in like a bit more detail and see how you can, effectively get, 1,000 digits of accuracy or n digits of accuracy, basically by using mystery rot and mystery rot to the 10 and mystery rot to 100 and mystery rot to 1,000 and all the way up to mystery rot to the 10 to the n, I don't know, a constant number of times, 120,000 times. And so if you ever get into a situation where you have like awesome speed up for like mystery rotation to the power of 10 to the n, then you could actually genuinely use this to get thousands of digits of accuracy for the angle. Okay, any questions? Okay. Let's roll the dice at this point. It's a 1 in 5 chance today. So we're going to have 6 for a win, 1 for roll again, and everything else is a fail. I don't know. I don't feel too good about it this time, but we'll try. No practice roll. This is the real roll. Oh my God, we got it. Oh, brilliant. Okay. All right, so our lucky day. We really hit these 1 in 5 chances. It's so great. Okay, so where's the tickets? Where's the tickets? Yeah, okay. Oh my God, this is so good. I feel we're pretty lucky. What are the odds? Okay. Okay, cool. Okay, here we go. We're going to draw it. This is good. Who's it going to be? There's a student who emailed me yesterday, and they said, I can't make the lecture tomorrow because of some reason, and it was an extremely valid reason. So I was like, oh, I completely understand. So then I said to that student, if you win the prize pantry, I will hold the prize for you. So this is still like an extremely low probability, but I have to warn you of that in advance. Okay. It'd be amazing if it was that student. Okay, it's not that student. The winning student is... All right, very good. All right, let's check the prizes. We got the cat, that's like some milk box. Got the novella called The English Understand Wool by my favorite author. We got quantum nail polish. And we got laser pointer plus polarizing filters. So what do you choose? Yeah, you were playing with them in my office hours, so it's perfect. There you go, 10 of the finest filters. And all laser pointers that are really cheap are advertised as cat toys. So cat toy laser pointer. Oh, this is so great. What were the odds? Okay, great. Cool. This is a tough class too to come to. So we're here and like it's cold, it's like minus something. It's the middle of November. We're doing like the most technical thing. So good job. Good job on coming to class.